Async await in Rust. That's the topic that we have, right? Okay, before I begin, I'm not going to go into all of the comparisons that have been performed, all of the previous failed attempts of, not failed attempts, but previous attempts in the Rust community to implement something like async await. I'm not going to jump into all of that because we have very little time. We're going to focus specifically on the current implementation of async await in Rust. Okay. Yeah. And then our goal is to effectively understand this and sort of understand Embassy, and then try to see if we can sort of implement it for one of our projects. Yes? Yeah. Yeah. So that's the goal. Now, async await. So there are some core, you can say, concepts that I'd like to introduce first. Okay. Some few pieces. So far, whenever I talk about asynchronous programming, the first thing that should come to your mind is, what is asynchronous? Right? What do we mean by asynchronous, asynchronicity, or whatever you call it? But basically, what does asynchronous really mean? Okay. Any ideas?
Asynchronous means it's not waiting for someone to finish its job and then it will start.
It's not sequential.
It's not sequential. Yeah.
Right. So one is, you can always say synchronous is, it's kind of easy and intuitive to understand. When we talk about synchronous, we say one after the other. Right? It's in a sequence. Correct? Sort of what we say. Asynchronous doesn't. Then you can just say anything that's not synchronous is asynchronous. Right?
Yeah.
Well, at least in this context, that is not entirely true. Right? Anything that's not synchronous cannot automatically mean that it's asynchronous. We'll talk about why that is, but first, in order to do that, we sort of need to have an understanding of what asynchronous means. Okay. Asynchronous basically means, the idea is quite simple. Let's actually look at a very robust example. And the best way, or the best place to sort of learn this is this blog.
Yeah.
This I highly, highly, highly recommend. Yes, there's a bunch of videos on YouTube that sort of talk about a lot of stuff, but all of them attempt to approach the problem from, you seem to have already worked on async await in the past in some other language. Let me introduce you to something in Rust. Right?
Yeah.
That the other sort of material that I've seen sort of approaches the subject from there. This blog approaches the subject from a place where it says, you don't know squat about asynchronous computations. I'm going to start from, what you probably know about computing generally, and I'm trying to draw, infer something out of that and build a foundation for you of what it means to be asynchronous. So this blog I highly recommend.
Yeah.
Okay, that's the first piece. Now, the second piece that I want to say is, when we are talking about async await, always remember this in your head. The first thing that you need to remember is, this is multitasking. This is something to do with multitasking, which means you have multiple tasks that you want to deal with.
Yeah.
Okay. If I get into the definition of threads and tasks, that will take up whatever time. We don't want that. Assume that whenever I'm talking about threads and tasks, assume that I mean the same thing for now.
Yeah.
Okay?
Yep.
They're not the same thing, because in many places they're very different. But anyway, multitasking is, I am performing, let's say, task 1. Then I have task 2.
Yeah.
Task 1 starts, progresses, and I'm right now here. Task 2 starts, progresses, and I'm right now. These are two independent execution contexts. You can say that. Yes? These are two independent execution contexts. Now, the problem occurs when, okay, they're independent. This guy doesn't know who this guy is, this guy doesn't know who this guy is. What's the problem? What's the big difficulty about this? Right? What usually happens is, it's like, I don't want to use an example. I'll just use normal examples. I don't know if you already got my flow, but I'm not going there. I'm just going to say, these two things want something.
Yeah.
Right? This is some data structure, some piece of data, etc. Right? It's two guys vying for one girl. Not going to work out well. Okay. So the idea over here is we have some piece of memory over here. Let's assume that this is a very simple 5. Okay. I have a very simple value that's stored in this memory location. And these two tasks are independently, sort of independent of each other. They're executing. And then there's this little 5 thing that I have. Both of them want access to it. You see the problem over here? Problem here arises when, okay, let's say I am reading from you. This guy is writing into this. Right? He's trying to change the value of 5 at the same time, at the exact same time I'm trying to read it from you. This is what we call the data race. And this is a basically undefined behavior. What happens, I don't know.
Yeah.
When he's reading, he can get a unicorn out of it. As far as we're concerned, we don't know what will happen. Okay.
Yeah.
And when he's writing, he will assume that he wrote something. He'll assume that he wrote something, but he doesn't know what he wrote. Probably he's setting the value to say launch missile or don't launch missile. We don't know. Maybe he thought he sent it. Maybe he thought he's going to bomb one country versus another one. He ended up bombing something else. He ended up bombing himself only. Who knows? That's undefined behavior. That's the effect of it.
Yeah.
Just giving you examples. Okay, don't assume that this is all only related to defense programming. Okay. So anyway, this is, by the way, this directly does not have much to do with async await, the examples that I've just given you. But just keep this mental model in your mind. Whenever you have tasks executing, right, the problem is always how do you share data? You have some shared data structure in memory. You want to share it. And you want to ensure that that shared data structure is, there's no undefined behavior when you're using it. Make sense?
Yeah.
That's like a picture that I want you to keep in mind. That's one. Now, in our case, when we actually talk about multitasking, there are 2 ways to do this, right? Actually, many ways to do it, but let's just say there are 2 ways to do it. In your operating system, you have multitasking. You have multiple applications open. They're all running. At least they all seem to be running at the same time. And then you also have what is called, so let me just say this. You have 2 types of multitasking. We call it, anybody?
Primitive multitask and cooperative.
Preemptive and cooperative. As the name suggests, preempt.
Non-primitive means also cooperative, right? Non-preemptive are different.
Non-preemptive does not necessarily mean cooperative. Okay. You can have other types of multitasking as well. Like, for example, I can say that preemptive is one, cooperative is one, let's assume. Then I can say that I can have a different multitasking where I say these guys will cooperate, these guys will preempt, or some hybrid, something I can set it up, depending. So these are the 2 widely talked about multitasking, you could say paradigms. Right? These are the 2 widely talked about, and pretty much everything stems from here. It'll be one of these 2. That's at least as far as my knowledge goes. So preemption. First, preemption is an actual English word. For all us non-English speakers, preemption is a word. Okay. It means interrupt. Okay.
Yeah.
It basically means I'm going to stop what you're doing. I'm going to preempt you.
Yeah.
Let me stop you there. Let me stop you there. I want to do something. I want to talk. Uday, I think your headphones are mute, right?
No. Speaker is on.
So there. That's it here, no? Fine. All right. So preemption basically means interrupt. I'm going to stop you and I'm going to stop talking or doing whatever, something. That's preemption. Cooperative means preemption. What is the primary requirement for preemption? Somebody that's stronger than you or has a higher level of authority than you can ask you to stop. Right? If let's say your son comes up to you and says, stop, what do you think is going to happen? Son says, stop to the father. Father is doing something very important. Son comes up and says, stop. What do you think is going to happen?
You won't listen.
More than that will happen.
Yeah.
Okay. So I'm just saying that preemption, by definition, you're saying that usually what happens is there's some kind of supervisor. Right? There's some kind of supervisor who is in a more privileged position, position of authority or whatever. That thing is sort of managing who gets to do what.
Okay.
Which of these tasks gets to run? Which of these tasks don't get to run? Right?
Yeah.
Yeah.
Cooperation is what cooperative multitasking is. We all say nobody's the boss. This is like open source. Everybody can do what the hell they want. Finally, you end up with some khichdi. Yeah. Finally, end up with some khichdi. That's one of the reasons why you should not be messing around when you are presenting. Okay. So finally, so what I was saying was cooperative is basically a little different. Cooperative multitasking deals with the fact that you have tasks that cooperate amongst themselves to yield control of the CPU. You say, okay, I'm done. Go ahead. You go ahead. That's you guys cooperate amongst yourselves to figure out things. Obviously, you know what's the problem with that? Okay, let me ask you this question. What's the problem with preemption? What's the problem with cooperation? There's no good solution or bad solution. It's just the fact that that's one design, this is one design. That's one paradigm, this is one paradigm. Let's start with cooperative, because that's why we'll be spending most of our time. Yes. Cooperative multitasking, what is the problem? I just told you that you guys can cooperate and each of you can yield. What is the problem? You guys, I asked you to work on some projects.
Someone doesn't cooperate.
Yes, somebody says non-cooperation is my motto. Then there is a problem. Right? Non-cooperative tasks can end up not yielding the CPU, and other tasks are starving for CPU time. They don't have access to the CPU. This one thing is gobbling up all your time. You didn't cancel that?
I informed Anish.
Okay. Just ping Arun and tell him that.
Yeah.
Cooperative is when you stop cooperation, that's a problem. Basically, that's a denial of service attack.
Yeah.
The other tasks, when they don't get access to the CPU, what does it mean? I am being denied access to the CPU. It means basically if CPU access to the service, I am being denied service. The other tasks are saying. That's the problem. Okay.
Yeah.
So one is not inherently better than the other. You decide which one you want to use. When you trust all tasks, right? It makes sense.
Yeah.
Let's say I'm the one who's building a system that's multitasking. Then I say, fine. I know I'm building the system, then all the tasks that make up my system are something that I've written. I know that they're not going to do any, hanky-panky stuff. So you can trust them. And I'd like to certainly build a cooperative multitasking system. Obviously, preemption, what's the problem?
only high priority task will get the access. Maybe the tasks which are low priority will keep on waiting only.
I just told you that preemptive multitasking, the only thing is there's some guy sitting in between doing all the mediation, saying you get it, you don't get it, you get it, you don't get it. Contrast that with our economy systems and our society. What do we get?
That is comes to father and father to
Okay, that's too far. But let's put it this way. Preemptive multitasking has a problem where effectively you're trying to preempt whatever is executing and then sort of move into the space, saying that I'm going to allow you, I'm not going to allow you, etc. Think about it very simply. The simplest way to do this is, if you think about it, preemption works largely speaking on interrupts.
Yeah.
Right? An interrupt comes in. When an interrupt comes in, you'll be like, okay, I'm going to stop what I'm doing. I'm going to service that interrupt. I'm going to get back to what I'm doing. Right? And that's preemption at a very fundamental level. But if you bring in multitasking into that concept and you say that there's an operating system, there's a scheduler that's doing the scheduling of the tasks, then the scheduler becomes very important. The scheduler is like the important piece of code that's sitting there and saying, oh, okay, I'm the one you have to get through. I'm going to decide when something gets to run and when something doesn't get to run. So that's a single target that I have. As an attacker, all I need to do is figure out how your scheduler is working and I can do a lot of stuff with it. Right? In practice, it's not as simple as that, but yes. The scheduler has been written and designed in such a way that it does, let's assume that it does round robin scheduling, which means there are 5 tasks. All 5 tasks, I'll say, okay, 1, 2, 3, 4, 5. Then again, 1, 2, 3, 4, 5. 1 runs, 2 runs, 3 runs, 4 runs. Right? I'm going to say this. Then I know that, okay, this is the fashion that this guy is running in. So let me try and see if I can sort of, just that single part of your system is what I need to mess with in order to achieve my objective. If it's good or bad, doesn't matter, but that's all I need to do. So that's like a single point of failure for you.
Yeah.
Right? Yeah. Like if you remove all the other stuff, like it can be bad, it can be good, etc. The single point of failure as well for you. Here, that's not the case. Let's say cooperative tasks. One of these tasks is not like it just assumes that that task just crashed. We'll just move on to another task. We don't care, right? It's not taking up the CPU, it crashed. So let's switch to another task. Right? That's sort of the thought process. Now, don't exactly think that that's exactly how it works, but just to give you an idea of what preemptive multitasking and cooperative multitasking is. Right?
Yeah.
Okay. Now, so this is a diagram of what preemptive multitasking does. So if you look at this, you can clearly see that. Can you clearly see, by the way?
Yeah.
Yes? Avina?
Yeah.
You're looking at your computer?
Yeah.
Okay, fine. So, if you see this over here, what's happening? We are basically saying that task A, there's a task A that's executing, and look at what task A goes through. There's 2 tasks. We are talking about task A1 and task A2, and then we're talking about task B. So there's program A, there's program B.
Yes.
Program A is spawning, let's say, 1 thread. 2 threads. Program B is spawning 1 thread. There's just an example there saying that task A1, A2 are 2 tasks that are spawned by program A. Task B1 is a task that is spawned by program B. Okay, let's start with that. What happens? Let's look at this first one. Task A1 now has control of the CPU. Let's say that it started executing. So that is moved into the CPU. Its code is being executed. task A2's code is still in memory. It's not moved into CPU. Assume that you have a single core CPU, just mental model, right? Same thing for program B as well.
Yeah.
Right? And the operating system as well. They're all in memory. Only task A1 is executing. Yes?
Yeah.
Now, suddenly, somebody says, I want to do something. There's a keyboard event, or there's a mouse click, or there is something that happens. There's a hardware interrupt that comes in. When the interrupt comes in, the CPU is like, oh, wait, I will stop executing A1. I'm going to stop right now. I stop. Then I simply, whatever the operating system interrupt handler is, that moves into, I basically jump to the interrupt handler, which means whatever code that was executing, I stop that, I start executing the handler, that moves in, right? Once the handler, and look at what happens. The A1 code is actually in memory, right? Correct?
Yep.
Now, when that is done, the interrupt handler is trying to say that, okay, once you're done handling, like once I've handled this interrupt, the interrupt handler is saying that I have to call task B.
Yeah.
So it pulls task B it switches over to task B and starts executing task B. So you see, you moved from one task to another task. You started with A1. Interrupt handler just assume that it's not a task, assume. And then you move to task B. That is, in a sense, preemptive multitasking. Whatever is running currently, you preempt it and you say, stop. I want you to handle this, you handle that. Maybe you'll come back, maybe you won't come back, depends on you. Depends on the interrupt handler. Right?
Yeah.
Okay. Key point over here. You are, when you're actually saying stop what you're doing and jumping to other places, the key thing that you do in preemption is you start saving state.
Yes.
Yes, because if I want to come back, I need to know how to come back. Right? There must be state information. That means what are my registers values at the time that I'm going to be switching? What is some important stack locals, etc. that need to be there? All of those things I need to restore the same environment that existed when I was jumping or switching. That is saving state.
Yeah.
Right?
Yeah.
Yes, making sense?
Yep.
Yes. So, and by the way, that switch from one task to another one is basically called context switching.
Yes.
I just told you that these are two different contexts. I've switched from here to here. So that basically is a context switch. Yeah?
Yes. Yeah.
Okay. And then you might also refer to these things as threads of execution. Same thing. Threads of execution. I also told you that, what's the other name that I gave it? I said, execution context is what I gave you. All right. So this switching that keeps happening, right? That you have to jump from here, then the operating system calls interrupt handler, then I have to jump here. This context switch actually adds up a lot of time. Not noticed. And first, I need to call the interrupt handler interrupts me. Then the state is saved. Interrupt handler is called. Interrupt handler processor executes. Then the interrupt handler calls whatever task it needs to call. It does whatever it needs to do. Then if it comes back, it needs to come back. So this entire round robin thing this merry-go-round thing that happens does take up time. There is a performance hit in preemption. All right. That's a drawback. Again, there's also a drawback of higher utilization of memory because of this state saving requirement.
Yeah.
Yes?
Yes.
All right. So all these things are actually sort of cons. The biggest con I would say is the scheduler is a single point of failure. Okay. Anyway, so yeah, this way it can guarantee that each task gets a fair share of CPU time without the need to trust the task to cooperate. This is essentially important when running third-party tasks or when multiple users share a system. But you notice I said something that The tasks, if they are trustworthy, then cooperation makes sense. What if they are untrustworthy? You are installing applications on your computer from the internet. Whoever, somebody else wrote it. If you use them, how can you trust them? Like somebody else's code that's been written, you are basically saying that's going to run on your system. Can you really vouch for them? Not really.
No.
Right? So in those cases, that's why all operating systems that are today mainstream ones are all preemptive. They're all preemptive. Okay?
Yeah.
All right. Anyway, so preemption and threads make up one of the fundamental concepts of operating system multitasking.
Yeah.
Cooperative multitasking is what we need to talk about, which is exactly where, we are going to talk about async await. Cooperative multitasking deals with cooperation of tasks. So you have task 1 and task 2. Task 1 executes for some time, says I'm done. You can take the CPU, and then you take it. And then the other task, then the other task. Like that, you just keep using the CPU. The idea is you don't keep the CPU idle. The important piece about computing is that you don't leave the CPU idle. You use the CPU to do compute, to do work. You don't block, you don't wait. That negatively affects the user experience. Right? Yes? Yes?
Yeah.
Yes.
So when we say tasks actually cooperate, the tasks need to know, they need to define their own pause points. Like I need to know when to stop. Okay? I'm executing. I said, okay, I'm going to give up the CPU, I'm going to yield. Right?
Yeah.
When? Under what conditions? Like what? Like you're done with this. How do I represent that? How do I write that in code? I simply say I put one statement over, say yield, we're done. Is that enough? Is the question. So that is where we sort of delve into all the other options. Async await comes into the picture, saying how do you do this? How do you define your pause points? How do you resume that pause? Like you paused over there, you want to come back. Like I'm done. For example, my task was to so I'm waiting on packets from the network. There are no packets. So I paused.
Yeah.
I'm saying somebody else wants to use the CPU, use Karlo by. Then I say AB. But I want to come back again, keep checking because I must have received a packet somewhere, no?
Yeah.
Right? So pause and resume is the problem that we need to solve. In order to do this pause and resume thing, we have async await and await.
Yeah.
We have coroutines in Go and C++, which is the same thing.
Okay.
The suspendable resumable functions are basically what you call coroutines. Okay.
Yep.
Go is like heaven for people when you actually go and look at Go. Okay, because it's very, very simple to sort of do this kind of concurrency over there. But effectively, we are talking about the same things. It may not look the same at all, but the concepts remain the same. Suspend, pause, and resume because I'm waiting on something is what we are talking about. Right? Okay. Then the other point that we should also talk about is saving state. All right. Here's the best part about cooperative. Look at just one thing you have to do. You have to only trust your tasks. If you trust your tasks, you get all these benefits. One is they cooperate, right?
Yeah.
One is they cooperate. Second is there's no concept of context switching and all. You're not spending time jumping from here to there, right? Save this, do that, do this, do that. None of that. So you don't use that much memory. You don't use you don't lose that much performance because context switching is basically switching from one task to another task is basically just the function just yielding. That's it.
Okay.
Go ahead, take CPU. Right?
Yep.
It's as simple as that. So it's very different. This is very fast. It's very low on resource usage. Right? Cooperative multitasking is that. You get those benefits because you don't save any state not much. The state that you need to actually save is very well defined, very clearly, exactly how much you need to save, what you need to save, you get to save that. More importantly, these tasks can all share a single stack, as you will see.
Cooperative multitasking.
In cooperative multitasking, it's like one big process, one big thread that has one single task stack. But that single thread is doing, actually, don't call it thread. It's like a single execution context where multiple things are happening in it.
Yeah.
But you're just using one stack. Yes?
Yep. Yeah.
So those are the benefits of cooperative multitasking, right? All right, and you already know what the disadvantages are. There's cooperation, there's non-cooperation, right? Yes. Non-cooperative multitasking can lead to things like denial of service, that can lead to starvation of other tasks and all the other problems that come with it. All right?
Yeah.
Now, with that out of the way, let's focus on async await. Right? Let's sort of give it a more concrete view from our concrete mental model for us. Right? Let's sort of do that. We anyway have it here, so I don't have to draw it. So here, if you look at it, there are two threads, the main thread and the foo thread.
Yeah.
Yes?
Yes.
Then there's the file system. Assume the file system is actually a different thread, but assume it's just there. We're not pretty bothered about it. It's just there. We are saying that main thread, read file. Main thread says, I want to read a file. It goes to the file system, tries to fetch the file, right? Then you go ahead and return the file. You're done. Yes. And then you wrote another piece in the same execution. You're calling foo. So you call read file first, then you call foo. Read file completes, then foo completes, then you're done, right?
Yep.
That's the standard way. That's what is synchronous programming.
Yeah.
Now here's the async way. We call async read file. We try to fetch the file. Again, go to the file system only. We are trying to get the file. The call immediately returns. Right?
Yeah.
I'm not waiting for the actual file to be returned. The function call has immediately returned. The async call has immediately returned. Once it returns immediately, at least according to my code, I can move on to the next job. Yes?
Yeah.
Right? So, but when I return, I have to return something, right? I don't have the file. I asked for a file, I don't have the file. कुछ तो देना पड़ेगा वापस. क्या दूँ?
It's the future.
I'll give you a token, which is called a future. Say, hold this, that value will be populated later on in the future.
Yeah.
Yes? That thing is called a future.
Yeah.
We are representing that thing as a future. Yes?
Yes.
Okay. Now, look at the boxes over there. If you see carefully, the time windows, the amount of time that it took. For example, here we saw that I don't have a laser pointer, but you see that.
Yes.
You can just move your mouse around. You see that the red bar over there.
Yeah.
Yeah. You wait for such a long time for the file to be retrieved from the file system, and then you call foo. Right? In the second case, you're not waiting for the file to be returned. You save that time. In that time, you can do something else while the file is being fetched.
Yeah.
Yeah?
Yeah.
That's the benefit of async await. That's why this whole hoops that we jump through for this, there must be something at the end of the tunnel. Why are we doing this? Performance. Right?
Yes.
Okay. So that is basically The idea of a future. The idea of a future. Right? Okay. Now, in Rust, what is this? In Rust, that concept of the future that we take, we simply want to sort of give it some, like, we want to basically talk about it in Rust. How do we talk about it in Rust? We say that, okay, whatever that thing I'm talking about, whatever is that thing, if it implements this future trait, it is my future. That's all I need to know. In other words, it implements one method. Say that poll. If it's pollable, if that thing that I'm returning, if it's pollable, then it's a future. In the sense that, remember, when I actually make the async call, I don't get the actual value back. I get something in its place, right? But the way to make progress, or the way to check whether that thing is, the file is ready or not, is to keep polling it, right? So all I need to know is that that thing that I'm returning is pollable, which basically means that does it implement the future trait? In Rust, if you want to attach some trait, if you want to define some functionality or behavior, you put it in a trait and you have the type implement the trait. That's the whole concept, right?
Yes.
Yeah. Types in traits. You basically put it in a trait and have that type implement the trait. Then you're done. That's exactly what we're doing. We want to sort of represent future, the concept of the future. In order to do that, the future needs to be pollable. That's all I need to know. So I just take the poll method, put it inside the trait, and I say, okay, implement this, then we're done. Right?
Yeah.
Make sense?
Yeah.
Okay. Now there's a lot more stuff happening in there. If you look at the poll function signature, there is pin, there is context, then there is this thing called the poll type. Right? There's a lot more stuff. We'll talk about all those things. But so far, everything makes sense?
Yeah. Yeah.
Yes. Now, if you look at it, the return type of the poll method is the capital P poll. Right? What is poll? It's already mentioned there. Poll is an enum.
It has two types.
It has two types. So the way I actually am getting to know if I make an async call, I get a future back. The future is of one of two types. Either I'm ready or I'm pending. That's the placeholder. So I can keep calling, I can keep polling until I'm ready. Until I get the ready value back, I can keep polling. Yes? Yeah? Makes sense?
Yeah.
All right. So that is futures. The concept of async starts with futures. Now let's look at how you work with futures. Now there's a lot of detail in here. I would recommend that you go through this. Per se, I don't want to jump through all that detail because we don't have that time. I'll sort of jump through the main pieces, which is what we directly use in Rust. Okay, which is what we use in Rust. If, for example, I kept talking about this cooperative multitasking, right? How do you create those sets of cooperative tasks? Right? How do you actually create those tasks that will cooperate amongst each other? How do you actually do that? Okay. Then here are the more rusty technical details of what we're doing. The way you define this concept, you start figuring out my cooperative tasks in Rust is you take your task, which is your function, any function. It could be some, by the way, functions in Rust this can be a block of code. It doesn't have to have the function syntax in front of it, or it can be a function. In front of that, you put the keyword async, like he's done it. You put the word async, that automatically becomes a cooperative task. Yes?
Yeah.
It's become a cooperative task. Now, what happens after that is foo implements. So if you actually look at if you actually go and ask the compiler to sort of expand this at compile time, what it does is it converts async function foo that on the top signature into the one at the bottom. Like we already know this, right? We've seen this before. We know that in Rust we have the syntax of function declarations are function, some name, and then I'll just give you a name, this thing, right? If I was to add async in front of it, right? And if I said something like there is a return type like U32, and then I said whatever's in the body, right? If I did this, then this would get converted to, when you actually get compiled it says function name this impl future, whose output value is U32, right?
Yep.
Yeah.
Yesterday only we talked about static dispatch.
Yes.
Yes?
Yes.
This entire thing simply means that I'm expecting a type that implements the future trait. Right?
Yes.
I'm also clearly saying when the future actually completes or is ready, what type of value am I expecting?
32.
That's what this output is giving us. Right?
Yeah.
Yes, everybody?
Yes.
So this is the first thing in Rust. What happens is you take anything that's async, you just add the word async in front of it. This is what's happening. That's it. Now the second part is when I'm actually doing this, what's actually happening under the hood is there is something called a state machine that's being generated. We'll talk about what a state machine is because that is where I want to spend some time for you to understand what is actually happening. How much time do you have? Okay. I'll try and wrap everything up in the next 45 minutes. There'll be a lot of information. Please be alert. Okay. Right. So you are alert. It is for everyone. Okay. So think about it this way. Look at the example, async function example string. Right? This example is an async function. You can clearly tell. Right?
Yeah.
And you can also tell that it is this function is calling other functions from within it. What are the other functions? The other function is nothing but async read file. Right?
Mm-hmm.
Those are the other functions. So those are the other cooperative tasks. Yes?
Yes.
Make sense?
Yeah.
In our fundamentals, we talked about cooperative tasks. So you start with this big block first. Then you say, okay, this is my thing. I'm going to put my cooperative tasks in there. So I'm starting there. I'm saying, okay, go read this file. The task that is containing, or rather, example, the function itself is an async, is a cooperative task in your head. Think about it that way. Cooperative task, which is cooperating with its other tasks. That's how we're building it. Okay. And the way that's happening is this. It is saying you have a start and an end. Look at the diagram at the bottom. The state machine, the way it's going to be built is like this. There are two functions over there. One is what? Async read file, which gets the foo text. Async read file, which gets the bar text. Right? Two different files we're fetching.
Yes.
Correct? So this particular asynchronous set of tasks, cooperative tasks that are that we just created, the Rust compiler is going to convert that and say, okay, let's start here. Let's say we start, there's a start point. Then I wait on
Waiting on foo text.
foo.text, I wait. Right?
Yeah.
Then I wait on
Bar.
bar. Sorry, wait. I wait on bar. Okay, not in the bar. Wait for the bar. Dot text.
You only.
Okay, by the way, all of this is being recorded, going up on YouTube. Okay, so saying that anyway. So this is the first thing that I want to like transform. I'm saying, okay, if I just wanted to look at it from a big picture and say, what am I doing? I want to start. I want to wait. I want to try and fetch this. I'll probably end up waiting. I want to fetch this. Probably end up waiting. Then I'll probably end up here. After that, I have to go through this sequence.
Yeah.
It is important for me to go through this sequence. Note that it is not, my logic is not telling me that it is okay for me to get bar.text without getting foo.text. That is not my logic.
Yes.
My logic is saying if, because once I get foo.text, I will use foo.text's length to determine whether I get bar.text. Looking at this thing, I read the file in. Once I get the file, I know the length of the file. I use that length to figure out whether the bar.text file is what I go fetch it. That's one key point I want to make, because some folks just confuse this, thinking that, okay, I was waiting for this, I didn't get it, so I got this. No. In this implementation, if you're looking at it carefully, these are set of, you can think of them as cooperative tasks, but the logic is very important. What you're trying to convey is this. Yes?
Yep.
Okay. So now that that's done, let's see how this state machine gets built. We're calling it state machine. It's a very nice name, right? All of you going back to your engineering days?
Yeah.
State machines, arrow marks from here to there, that to there, states and transitions and all of that.
Yeah.
Right? We're basically going to talk about that. A state machine is nothing but a collection of states and the transitions between them. That's all. Nothing else. Yes?
Yes.
Yes.
So, when you talk about programming languages, what can be states?
Initialization, waiting, something like that.
Much more simpler. What can be states? Okay, not binary. Huh? State. We just talked about saving state and all, no?
Running state.
Program states, right? We're basically talking about program states. At this point, I have this data structure in memory. I have this in memory. I can probably move from here to here. This operation is allowed. This operation is not allowed. Those things are what we can talk about. So let's see how this thing gets built. So before I jump into this, I want to say that this is a very close approximation to exactly how the Rust compiler does it, but it's not the same. One big difference that happens over here is Rust uses what's called generators. Okay. For convenience sake and to understand, we are not touching on what generators are, but this is exactly how they work. Okay. That's one point. So once you have this, now let's look at this. Here's what's happening in a more detailed way. So I told you there's a start point, right? Think of the start point as the example task. The example task is a task that can return a future, which means it can be polled, right? So the start step one, poll that. See that start? Poll. Immediately when I poll, what is the next step that I can go into? If you were to look at the example here, see the example at the bottom. See here, example started. I polled example task. The next place where the next cooperative task comes up is foo.text. That making sense?
Yeah.
Yes. Not clear? What's the question? Think about it. What's your question? Okay. So I just said that you have example task, right? Think about it as example is a task. I told you that there are inside this, how many other cooperative tasks are there? Right? So in total?
For start and
Start is one. Example, there are two. Then end you can forget. Three. Right?
Yeah.
There are three tasks. That's what we're saying here. Correct? So I started at one. I polled the example task. Now what I'm saying is when I poll, according to the logic of the function, where is the next task that I will end up with?
With the first row.
Correct. Once you hit the first foo.text, once you hit the first async read file, that's the one that you end up in. And you say, okay, do I have the file or not here? I don't have the file. Okay, I'm just going to return pending.
Yeah.
Yes?
Yes. Yeah.
That's what's happening on top. Foo.text ready or not? Question mark. If it is yes, then I take one direction. If it is no, waiting. Waiting. I do not go forward from here. Logic says don't go forward from here. I do not go forward. I'm waiting. Okay.
Yeah.
If it is yes, then I go. Okay. Then again waiting for bar.
Yeah.
It will stop that.
I will come to the part. According to this logic, I am pending. I have returned a pending value. Okay. I've returned a pending value. That's all I've returned, nothing else. Now, once I've returned the pending value, so let's say the first one completed. I forgot the first file. Then I use the first file to basically jump into whether or not bar is ready. Right? If bar is ready, fine. I'm going to go forward. I'm waiting for bar now because I asked for bar. Bar has not been fully fetched. I'm going to wait for it. See there are two more poll calls at the bottom.
Yes.
All right, I keep polling until I get it. Until I get ready, I keep polling. So that is the high level state diagram that you would draw in your mind and that you need to implement.
Here the polling in a sense it is a if condition, not a while polling what we do, right?
Yeah. So you don't think of it as a while. Don't. That's a busy loop while was what you're thinking. No, we're not doing. The whole point about async await is you don't do busy waiting. Right? You don't busy waiting. What happens actually, I'll give you an example as well. This is one future. Okay, this is one complete future. Right? What happens is there will be a executor which will have a queue. In that queue, there will be future 1, future 2, future 3, future 4, future 5, future 6. I paused over here, so I'll jump to 2. Do some other task, some other future like this, some complete future. I'm going to start doing 2. Choose pending, I'll go to 3, go to 4. Getting it?
Yeah.
So these entire futures get collected and stuffed into a queue. And then you start pulling stuff from there if one is pending. Just keep moving to the next one. So you're not waiting.
all tasks put it in loop that will match whichever is ready feature.
Correct. You put all the futures, like for example, this entire future that you saw, that example function future, that is one future. All the sub cooperative tasks are also sort of part of it. That's one future. That entire thing is one future. Then you created another one that is doing some other job. That's 2. You push them both into the queue. This, depending on which one returned pending, I move to the next one, or I say, okay, this is ready, I push it out of the queue, it's done. Then the second one just becomes my first, something like that.
All of them are running simultaneously.
So simultaneously means that there's actually, if you have a single core, nothing can run simultaneously, right? If you, the only thing that what you're referring to is parallelism. I can run things parallelly when I have more than one core. If I have a single core, I will try to do simultaneous multi-threading, or what is called one after the other interleaved. I will try. So let's say I'm doing two tasks. I do one task a little bit, then another task, then another task, then another task. It will feel like both of them are running at the same time. Okay, that is called simultaneous multi-threading, SMT, but that is not parallelism. Parallelism is basically executing parallel. Two things are happening at the same time.
It's not possible in single core.
It's not, because you have one core. You can do one thing at a time, right? Make sense?
Yeah.
Okay. So now this thing is what gets converted to our state machine. Now this is where the whole Rust community is like the smartest people. The community come together, they say, let's do it this way, let's do it that way. There's a debate for 3 years, man, that went on, which is very good. And they put together this this async await, which honestly I think is this is the best open source at work example.
Okay.
Right? There's a lot of work that went into this. I can actually vouch for that. Because I didn't contribute much, didn't have a lot of time, but I was reading everything. Anyway. Okay. All right. So far you understood that part. Now let's look at this. Now, the state machine, the way it gets built is like this. That same function that you just saw, you simply say, okay, there are 4 states. There's a start state. I'm waiting on some foo state. I'm waiting on some bar state, end state. All those states are represented in an enum, saying I can be one of this entire state machine can be in one state at a given point. Right? I can either be in start, either waiting on foo, or waiting on bar, or I'm done. One of these states. Then I start that. Then the first thing I do is I implement future for the example state, like the example function. Correct? Yeah. That's the first state. I implement that for the example, for the state machine. Right? Make sense?
Yeah.
The implementation is extremely simple, at least here. In reality, it might be a little different, but it's the same thing. Okay, you see that you are saying, I'm just going to match on self. When I poll, I'm going to match on self, which is the state machine. I match on it. I just look to see whether, okay, am I in start state? Am I in waiting on foo state? Am I waiting on bar state? Am I in end state?
Yeah.
Right? Mm-hmm. That's all I do. Nothing more. Making sense so far?
Yes.
Now, the important thing over here is this is all the Rust type system coming to the picture. Each of the states has some type of value associated with it. You see, start has start state, waiting foo text state has waiting foo text state in the brackets. See that? Then bar has bar, waiting on bar text state.
Yeah.
Yes? Yeah. So some state information is also attached to each state in my example state machine. Yes?
Yeah.
So far?
Yes.
Yeah.
The point is what? If it implements the poll function, it must return what? A poll type.
Poll type, yeah.
Poll type can be ready or pending. That's all I'm looking for right now. It's ready, that ready will contain the value. If it's pending, it's just pending. Right? Yes?
Yep. Yeah.
Okay. So, look at what happens. Step 1. Step 1, we're saying you are matching on what? The match brackets that you saw, Here, they're empty, right? They're just saying dot, dot, dot. This means there's something in there. I'll talk about it at the bottom. That's what he's saying in this blog. And look at the first example. The first match arm, what is he doing? He's simply saying, okay, I'm in the start state. I'm the start state. Now, if I'm in the start state, then my next step is to go get the file foo.
Yeah.
Right? Make sense?
Yes.
Yeah.
So I'll simply go ahead and call async read file.
Yes.
And whatever I get, I'm going to get a future back. I'm going to get a future back. Once I get that future back, foo text future, I am simply going to stuff it into, simply going to create my waiting foo text state. Is that making sense?
Yeah.
Remember, in your example state machine, just keep a track of this in your head. In your example state machine, on top, just to point your cursor, in your example state machine, you see that waiting foo text. Waiting on foo text has inside the brackets, it has waiting on foo text state. Right? The first match is going to create that type. Making sense?
Yes. Yeah.
Now scroll down.
You are sharing.
No, it's your sharing.
Sorry. All right, then that means okay, that's okay. So waiting on foo text over here is the type, this particular type, right? Now this type, if you watch closely here, I basically go ahead and in the first match, I basically go ahead and say, read the file. I'm going to get a future. I know that for a fact. It'll immediately return a future. Okay. Even if the file is available, that's another point. Even if the file is available, let's say that file is 1 byte or whatever it is. It's available, it will immediately return. It will give you a future, first thing. That future, what I did is I put it in this struct called waiting foo text state. All right. And I'm saying, what I'm basically trying to say is, this is the state that I need to move forward. This is the only state that I'm going to store on the stack that is required for my first file read. For my first cooperative task, he only needs this. He only needs this. This is the state that he exactly needs. So I'm going to sort of capture this and maintain this so that he can use it in the next match you will see. Okay. And that's exactly what happens. In order to move forward, the poll function, when you call it, obviously when the first poll gets called, the first match triggers. Correct? Because when the state machine started, it was always in start state. Correct? So this thing will get triggered. Right? Making sense? Everybody?
Yeah.
So it will get triggered. When it gets triggered, we are resetting the state machine state. We are setting it to waiting on foo text. Move to waiting on foo text is what we are saying. Correct?
Yeah.
And we are including the future inside it. Correct?
Yeah.
Yep.
And then what we've done here is, now when you move to the next state, because you already set it, when you do the match now, you're going to go ahead and come into the waiting on foo text state. You will match on this now. Correct? The next time you poll, you'll match on this. Yes?
Yes.
When you match on this, here's what's going to happen. Whatever future you put inside your foo text state, that is going to get pulled because that's a future, no? Yes, because that's also async file read. That's an async function actually. Yes, everybody?
Yeah.
Async file read itself is an async function. That's why it's asynchronous.
Yeah.
Right? So that itself will get polled. Now, when it gets polled, I can either get pending or ready. Yes?
Yeah.
And that is where I'm putting, if it is ready, go ahead to the next step. Go to the next step. That means get the future for the next step, put it in your state, and then when you get polled again, you can call this guy. Right? Now you're moving through. Making sense?
Yes.
Yeah.
If it's pending, you do nothing, you just pause. You've paused. Here, when we saw in that queue, you saw that there's this thing. We're paused. We'll try and move on. The executor is another concept that I'll introduce. We'll move on to the second future. Okay. Yes?
Yeah.
Yep.
All right. So that makes sense. Now the same thing repeats itself for bar. Yes?
Yeah.
This is what bar looks like. So once bar's state has been set properly, then when you poll for bar, this is what happens. You either get to the end state, or you either get to the end state or you don't poll pending, depending on whether the bar text is ready or not. Yes?
Yes.
And then the last state is the end state. That's it. That's the full state machine. This mental picture, if you apply it to anything that you see that says async function, blah, everything will make sense. All the await points are pause points.
Yes.
All the await points are simply pause points. Right? They can be resumed at some other, whenever they're ready to make progress, they will be resumed. But the important thing is to poll them. That is the important thing. Yes?
Yeah.
Make sense?
Yes.
Questions? Any questions? Nothing?
No.
Anyway, take some time. You have to digest this a little in your head so that it makes sense. All right.
Yeah.
Then you have pinning. Pinning is another concept that we haven't touched. Pinning is a very simple point. It's nothing extraordinary, but a lot of time was taken to actually sort of land on this particular API. Pinning is a concept that says in Rust, you know that, not just in Rust, but in any programming language, it's possible that you can have things called self-referential structs. For example, I have a struct. I'll just make it very simple. I take this example only.
An example.
Take this example itself. In this example, if you see closely, okay, forget this example. I'll just show you something very simple. You have a struct. Okay. Struct. Whatever. Struct is some struct. You have a value. Some array, you have it in there. Okay. Like you say, you have an array in here. Something like this. Okay. And then you have another field in there that says address. And that address is pointing to, it's referring to array. Element 1.
Yeah.
Okay. This is a struct. The first field is some array. The second field is pointing to the first
Array.
the
Element in that.
of this.
Yeah.
We are holding an address. We're not holding the element. We just have a reference to it. Okay.
Yep.
The problem is when you do something like this, if it ever gets moved around in memory, then the address has to change here. Is that making sense?
Yes.
Yeah.
Because you're not actually talking about values anymore, you're talking about addresses. Right?
Yeah.
Self-referential structs. You're referencing to some element of yourself. And particularly that is probably in some address that we are trying to refer to. When you try and move them, you can have all sorts of problems because the address changes underneath it. Okay, if I moved this is a problem. This becomes a problem because this address change is probably referring to some crap. some uninitialized memory it's referring to. Right? Yes?
Yeah.
In short, that is self-referential structs.
Yes.
Okay? And when you saw that example state machine you saw, we saw that you were building all those structs, waiting on footex state, waiting on bartex state. When you're actually building the state, you'll come across this kind of self-referential structs a lot.
Okay.
So the solution that they came out with is what they said was, we can't move them. Well, if you read the blog, he'll tell there are multiple options that they looked at. He said, we can't move these things. That is where the idea of pin came into existence. You are pinning it to memory.
Can't be automatically update the
Yeah,
address.
that is one of the things that they've discussed in there. But in order to do that, there must be some extra code that's keeping a track of that. Rust folks will never agree to extra code running in there. That is what's called zero cost abstractions. You don't need to have garbage collectors, this and that. We must be able to do it as, like people who want this should not pay for something that they don't want to use. Yeah.
Yeah.
That's why that's possible, but that was not used. So we came out with pinning. Pinning is saying that self-referential structs are not supposed to move.
Yes.
Okay, that is why you see this. Where is it? Here he explains with some diagrams and stuff exactly what happens. And this is to your Lavanya's point, where you're saying you update the pointer on the move when you move, or you store an offset. There's another option. These are three options that you have. Forbid moving the struct. They chose the third one. Okay. Anyway, I was just trying to look for that. Where is it? Let me go top. Acha, pause. Just pause.
1 second.
Okay. Generally, you would have just seen what's called.
Feature.
Yeah, you would have seen mute self, right? Generally, that's what you would have seen. But here you see pin mute self. So that whatever that type is.
The feature is pinning.
Yes, what you're saying is whatever that self is, it's being pinned to memory. That's what pinning is. So if you try to move it, it's going to be a compiler warning, error, not warning.
It will be compiled and error.
Yes, pin is officially been added to the compiler. So if you wrap something in pin and try to move it, you're going to get a compiler error. By default, everything is unpin. Default is everything is unpin. But specifically for self-referential structs types, use cases that you have, put it in a pin. Yes?
You can change the contents.
Yeah.
But we can't do it.
You can't move it.
Okay.
You can't move it. Which means any addresses, etc. should, if you're pointing to something, referring to something, that will remain the same. But you can update the values as such. That's it. Right?
Yeah.
Okay. So far we've come all the way to pinning. So pinning is kind of done. Then heap values, all of this is extra stuff. I highly recommend that you read it. Stack pinning is a little complicated. Fine, it also exists, big deal. By the way, this pinning usually is only, you pin it not on the stack, you pin it on the heap.
Yeah.
All right. And that's why there's a specific mention over here about stack pinning, which is also sort of possible. But I haven't seen it used a lot in many places. Anyway. All right. Then we have, we already saw on this post, pinning and futures, fine.
Executors.
Yes, let's get to the executors part. Now, once we understand executors and breakers, these are the entirety of, at least the foundations of async await is something that you know now. once you understand executors and wakers. Yes?
Yeah.
Slowly, if you start looking at the signature, you'll start getting what I'm saying. The poll function that you see, we talked about self-referential structs and pinning. We talked about polling as a concept itself to make progress. And then we are going to talk about executors. Then we'll talk about wakers. So the context that you see over there, the CX,
Yeah.
that is basically to do with your wakers. Okay. Very simply, I will explain the concepts to you. I will not dive very deep into it because of paucity of time, but I'll give you a heads up on essentially how you're supposed to think about these things. All right. So before we go forward, let's take stock of the situation. So far, so good. Any questions? Futures, state machine, pinning. Right? Makes sense.
Yeah.
Okay. Yes, Yashwant.
Yeah.
Good?
Yeah.
Yes. Okay. All right. So the next piece that we have is what we call executors and wakers. All right. Right. I'm not going to jump into the large details of this. There's a lot of stuff around building an executor efficiently. Tokyo is one. The async standard is another one. Then embassy is for the embedded world. That's what we are going to focus on quite a bit. Then there was a whole bunch of work on this. There was a small executor that was built, small SMOL, which is very, very, very good to at least learn. Very easy to learn. Okay, small. So lots of stuff. So executors can get really complicated. That's what I'm saying. What is an executor, first of all? An executor, as we are saying, I keep saying poll, right? Somebody should call that poll method on the future.
Yeah.
Right? Who is that somebody? That somebody is the executor.
If poll returns pending, it will switch to next future.
That's future. Makes sense. So we just saw that, right? That's the simplest way I'm going to explain this to you. We can sort of elaborate on this if required, but I'd like to move on. Okay. Essentially, you can think of this, the executor, as it has a data structure, something like a queue, and you can keep shuffling futures into that queue. Right? The job of the executor is one thing primarily. Of course, there's a lot of complexity involved. It takes the future, but calls poll.
Yeah.
Sees whether it returns pending or ready. If it returns ready, pull, throw out, we're done, go. If it returns pending, either you push it to the back of the queue, tara ke things you have to do. Okay? Then, if it returns pending, you push it to the back of the queue and then you go to 2.
Yeah.
Simplest design. Just leave it there. Right? 2. Then, same thing. You keep running through futures. You're like a wood chipper. You keep throwing wood into it, it'll keep chipping it. It's all it cares about. Right?
Yeah.
The executor's job is very simple. Execute stuff. Here's the thing where you keep coming into, you talk about things like Tokyo and all. What happens is, if I have to execute something, I need to be able to, sort of pass it to some operating system thread or something, right? Correct?
Yeah.
That's where this concept of a thread pool and all comes in. Load onto a bunch of threads, and it has this queue. It'll pick one from here and give it off to one thread. That thread will run that, it'll try and poll the future. Depending on whatever happens, there's updation that's happening. Okay, so this queue is not this simple. Obviously, there are so many threads that are trying to read and write from here.
Yeah.
There are so many threads that are trying to read and write from here. There's a lot of synchronization that's required. So that's where the complexity comes in. Why microcontroller you have only?
One thread, one CPU.
The whole point we're saying is you can have more than one thread, right? Because if I think about it, if I actually create an executor that will allow me to create multiple threads, I can start giving work out like this. So I designed the executor to just give me threads. In the microcontroller setup where bare metal, there's no operating system. We come out with threads. We come out with our own abstraction of creating threads. All we need to do is the executor, here's the thread, go. Here's the thread, go. Right? So that's the point that's happening over here. Making sense? Yeah. That's the simplest thing. Now, the other part that we keep talking about is, fine, you got your executor done, it's working, it's all fine. I said, what if it returns pending? How will I know to repoll it?
Wakers.
So that's where the wakers come into the picture.
Yeah.
All right. The waker is something that is passed into the context of that poll signature. What we are saying over there is, when you run this, and while it's pending, please register this to be woken up. Effectively, what you're saying is that is where so in our case, the executor won't push it to the back. The waker will just reschedule it. The waker will take that future and just reschedule it back into something like this queue. Get it? The waker takes the future and puts it back into the queue. At some point, it'll get polled again. Yes?
Yeah.
Questions? Very nice, no? People are playing around with what? Nice little queue of balls. They're juggling it around, saying, okay, let's do this, let's do this. Feels like that, right? Yeah. That's kind of what programming is, by the way. Keep trying, keep trying, keep trying, something will work.
I have one doubt in this case. While doing all this thing, doesn't the priority takes the backseat?
Which priority?
Like the priority of a task.
Achha, we're not talking about real-time systems. If you've never heard me say priority,
Yeah.
right? There's no such thing here.
Okay.
In cooperative multitasking, we're not talking about priority. We will talk about it when we talk about empathy.
Achha, okay.
All right. In empathy, the simple twist that they gave is you build many executors. Assign executors priority.
Every task they'll use interrupt.
Okay.
They will just say that, okay, priority concepts don't matter here. So let's actually create multiple executors and then assign them priorities.
Okay.
Yeah. So if I get a high priority task that comes in, I push it into a high priority executor. Something like that. That's not exactly completely how. We will learn about it. Even I have to read about it. But yeah. Agreed?
Yeah.
These are the concepts, questions. There's a lot more stuff in the blog. This queue, there's an entire page about the queue itself saying, you know, there is this double-ended queue called a deck. All right. Then in order for you to access the queue, you need to ensure that it's synchronized because there's so many things that are accessing this one data structure queue, right? So if you're reading and writing simultaneously at the same time, who's doing what? And this is happening at the speed of thought, literally microseconds, milliseconds, whatever. People are, the things are accessing and doing stuff. You need to figure this stuff out. So there's atomics that come into the picture. Atomics, these are essentially speaking hardware specific instructions that you get. You get access to hardware specific instructions that say, that's the only way to deal with multi-core programming and to deal with something like this, where what you're trying to say is, A good example is like this. I can say that on a single core, let's say I want to go ahead and okay, on a single core, if I get an interrupt, it is only that single core that I'm interrupting. All right. So if I disable interrupts and I just sort of run my code, it doesn't mean that on a multi-core system, I'll get the exact same behavior I'm thinking. Multi-core system has more than one core.
Yes.
So I only disabled interrupts so that I have access to some piece of data. No other thread has access. Assume. But if you have multiple cores and you disabled interrupts, then the other core can probably sort of mutate your value here. So what these processor guys did was, actually not processor guys, but the industry did was, that's why we talk about atomics. We're saying that we want to atomically change the value of something in memory. Okay, some piece of memory, I want to atomically change it. Matlab, atomically, the word atomically means there are no intermediate states. I did it or I did not do it. That's all. So those instructions are called compare and swap, fetch and release, and something like that. A bunch of them. I have to keep reading them just to remind myself that this does what, that was what. Atomic programming with atomics is not easy. It takes time, takes effort to understand. But the concept is very simple. It is to say that I want to atomically, let's say I want to atomically increment one. Okay, there are multiple threads that will probably have access to that one. Okay, there are multiple threads. If I use atomics, one is I can use these synchronization primitives like what you just saw. What you just saw, which is I can use the mutex. I can use those things. That's one. The second piece is I can use atomics. In some cases, you only can use atomics.
Yeah.
Right? Make sense?
Yes.
So that's where we're going with this. All right. Anyway, I lost what was the track of what was the question actually?
Multiple priority tasks.
Priorities. Anyway, so priorities, I thought I said, we'll talk about it in embassy, which is tomorrow, but I hope you got this much.
Yes.
Yeah.
The difference between multi-core programming versus single core programming, the important thing is atomics. You cannot do programming on multi-core systems without atomics and expect to be synchronized.
Can you think of any example of atomics and mutexes, like where atomic will be fit and where mutex will fit? Like as for me, both are serving the same purpose, right?
Mutexes are actually built on top of atomics.
Okay.
All right. So, yeah, put it that way.
If we put it simply, the register type will define what is atomic data type.
Register type.
We can update the register. Multiple functions can update that register.
I don't think it's not a register thing. We're talking about memory.
Yeah.
We're talking about updating or rather accessing memory when number of threads are contending for the same piece of memory. Okay, we're not talking about a register. We're talking about memory, first thing. And when you want to ensure that read, write, modify behavior is actually what I intend it to be, then you need something like atomics to say that. What are atomics doing? They're basically instructions. What do? They basically say, if once I hit this instruction right in memory, everything before and after that sort of is guaranteed to be atomic. That's sort of what is the definition of what's happening over there. That means the processor itself, the instruction set itself is dictating to the processor whether you can do something or not. So there's no way any thread can go ahead and affect, something.
Yeah.
All right, we'll talk about atomics a lot more. I'll need more concrete examples to sort of separate them out. But yeah, That's the point.
Okay.
Okay? Any questions? I'm going to take my seat. Yes? Okay, there's quite a bit. There's, a lot of stuff over here. And then he comes down to a very concrete example. He gives you things like how do you build a keyboard driver that takes input and then prints it to the screen.
Yeah.
He gives a very nice little introduction. He uses something called the crossbeam crate, which provides these kind of interesting cues and stuff so that you don't have to implement it yourself. A lot of this information is available in the blog. Quite lengthy, but at least my opinion is that as far as async await is concerned, this is your Bible for the initial basics.
Yeah.
Okay. When you get to things like Tokyo and all, you might have to look up, you can read the documentation and all that, and you can sort of ask for questions, ask for help and stuff. But the basics, to wrap your head around it, this is it.
Yeah.
Yes?
Yeah.
All right. I think that's about it. If there are no other questions, we'll stop recording.